All right, guys. Hey, welcome back to another lesson. Today we're going to talk about applications of similar triangles and polygons. I'm going to come up with 3 examples that we're going to work through. My lesson notes, which are online, goes through more examples, so feel free to look at those and work them out yourself. And always ask questions, okay? So we're going to jump right into it. Some of this is basic, but we're going to lead up into, I think, a concept that isn't primarily discussed in the lower grade levels. So let's just get into it. All right. So example 1, we have here, Nick is estimating the height of a roller coaster located in Ohio. Nick is 5 feet 3 inches tall. His shadow is 3 feet long. The length of the roller coaster shadow is 40 feet. How tall is the coaster? Now you're probably thinking, shadow lengths? Really? Are we going to mess with those? We can use those for some level of accuracy. Okay? And like I said, this might sound similar to what you've done in the past. So what I did is I drew a picture. So here's Nick, and here's my infinity roller coaster that I drew up there. Okay? And notice I drew right triangles. And why did I do that? Besides that it works nicely if I do. Well, the height is the perpendicular side of the vertical side, of the triangle. And the base for both of them would be perpendicular to your height, right? So 3 feet, 40 feet represents the shadow lengths for each object and person. And then the vertical side are the heights, which I want to figure out, right? Now you notice, yeah, we have 90 degrees here, but what other angle do we have involved that makes these guys similar? Well, we're talking about shadow lengths, right? So we're talking about the sun hitting this object in person, okay? So that the angle that they're, getting hit by with the sun is one angle that they are congruent to at least. So we have 2 angles for both of them. So we could say that these guys are similar by angle, okay? It's always important to note if you can solve a problem by similarity principles. I can't here using angle. Now we just set up the fractions. One thing I want to clarify here, Nick's height's 5 feet 3 inches. If I'm going to be multiplying, I can't multiply feet and inches by feet. Not going to work. I have to do a conversion here. So 5 feet 3 inches, what would that be as a decimal? Well, a lot of people might jump to, isn't that just 5.3? Not quite. Think about this. 3 inches out of 12, right? 12 inches make a foot. So 3 inches out of 12 is a quarter, right? It's 1/4. And 1/4 as a decimal is 0.25, okay, or 25 hundredths. So in other words, this comes out to be 5.25, or 5 25 hundredths feet would be Nick's height, okay? So I have to do that conversion first before I start setting up a proportion. Now, could you find a scale factor and therefore find the height? Absolutely. Because we're just kind of continuing the theme of the other lesson videos and problems, I'm going to set up a proportion. So what I'm going to do is I'm going to put the heights together. There's a lot of ways of solving this, by the way. This is just what I picked. So the heights are similar. So 5.25 for Nick's height. The roller coaster's height, I don't know. I'll put X. And then over here, I'll put the shadows together, their lengths. Okay, they're going to be similar to each other by the same similar scale factor. So then I'm going to have 3 feet for Nick's shadow and then 40 feet for the roller coaster. Now notice I put Nick and then the roller coaster at the bottom, Nick, roller coaster here at the bottom. You have to be consistent with setting up these fractions. Now we cross multiply. So this would be 3x. And on the other side, 40 times 5.25. Let's see, that's going to be 210, I believe. Okay, double check my math. And then for the last step, divide both sides by 3. So x comes out to be 70 feet. Okay? So the height of the roller coaster would be 70 feet tall. Okay? So nice example just to show you how we can use triangles and more of just an application element. But the process for solving it is still the same, huh? Doesn't really change that much. What do you think? Pretty cool, huh? All right. Now, let's do something a little bit different. Let's talk about this guy. Okay. So like I said, I am jumping around with my examples. So we have here the measure of two supplementary angles are in the ratio of 2 to 3. Find their measurements. Okay. Let's go ahead and do that. And let's draw a picture. Okay. I'm always a fan of drawing something. I think it really puts things easier in perspective. Now, they're supplementary, right? Okay, so there's two angles that add up to 180. They could be linear angles, right? So let's say I have a pair of linear angles. When I put their measurements together as a ratio, I get 2/3 out of it. Now, I don't know what one of the angles are, right? So I can put it as an x. Don't know what one of them is. The other angle, what would that measurement be if I don't know it? Well, to get to this angle, I would take this guy and subtract it from 180, right? And that will give me the result of this angle. It's so weird, right? Because it's like, I don't have any measurements, but we could still work with it. I don't know this guy, but this guy would be 180 minus x. And then if I know what x is, I know exactly what those measurements are. Now, since the ratio to this guy is 2/3, their measurements should be 2/3, right? So what I'm going to do is I'm trying to figure out what values would make this guy 2/3. I'm writing it as a proportion, okay? Cross multiply to solve, so this would be 3x. On the other side, we get 360 minus a 2x. Remember, you have to multiply that out through each one of those, okay? Wait, so far so good? I think we're doing fine right now. Yeah, we're doing good. Add 2x to both sides. So 5x equals 360. Okay, my last step, divide both sides by 5, and I would get 72 degrees. That's just one of the angles, right? That's this guy right here. This has become 72 degrees. Now, what angle would go with it? Subtract it from 180. I get this guy to be 108 degrees, okay? So if I were to replace this with the two angles that I came up with, I could see that if I were to reduce these guys, I would get 2/3 for that guy. Or if you want to divide both in your calculator, see if you get the same thing, you will, okay? So once again, I think the picture does a great job. If I were just to say this concept without the picture, it might be a little bit more difficult, okay? Pretty good. Sorry, I'm a little stuffy. Springtime, right? All the allergies and stuff are coming into play. Makes it quite an interesting seasonal change. Okay. Now, we have one example where there's some triangles. We have another example just messing with some angles. How could similarity be used with this? Now we're going to talk about perimeters. Okay, now I don't need the PowerPoint, so I'm going to exit out of this guy. Come on. Don't need the PowerPoint. There we go. Now it's just me and you. All right? Let's talk about perimeters of similar shapes. They have a very unique property. Okay. Oh. There. All right. We'll get to this example later. All right, let's talk about just a fundamental principle. The perimeter of similar polygons, okay, are proportional to the scale factor between them. Okay, kind of weird, right? Let's just do a basic example. If I had two triangles, make this guy 2, 4, and 6. To make them similar, I multiply everything by 2 here. So this would be 4, 8, and 12. Okay? The perimeter of this guy here, let's see, 6 and 4 is 10, plus 2 is 12. The perimeter of this guy over here, 8 and 12 is 20, plus 4 is 24. Now look at this. My scale factor is a 2, right? I just established that. If I multiply my perimeter by 2, I get the other triangle's perimeter, right? Just by a basic example, we can see that this relationship is working. So what I'd like for you to do is, well, let's look at a small proof of this, okay? So up here, let's see if we can't match this behavior. I have 2 quadrilaterals, okay? And you can tell that if I multiply everything here by a scale factor, I get this guy up here, okay? So my perimeter of ABCD would be my scale factor times J plus my scale factor times K, scale factor times M, scale factor times L. At the very bottom, my perimeter would be, for the bottom, for JKLM would be J plus K plus L plus M. Okay? I'd just be adding up all those side lengths. And actually, I apologize. I should make this proper, sorry. Let's do this. S times the side length, JM, S times the side length, ML, sorry, S times KL, and then S times JK. And down here we have JM plus ML plus KL plus JK. 2 sides. I'm sorry, a side needs 2 points. I better make it specific, okay? I know a lot of people are saying, why do you make it like A, B, B, C, and so forth? Well, you'll see. Now notice, at the very top, I could factor an S out. They all have an S in common. So let me do that. So if I factor an S out, look what I have remaining. Look at what happens. When I factor that scale factor out of this guy, I have the original coordinates, not the original coordinates, the original side lengths as this guy. So then I can cancel out those values. So what am I left with? S, which is the scale factor. Okay? So this is like a small proof to show that what we witnessed here is always going to work no matter what the shape is. Kind of cool, isn't it? So you don't need to know all the measurements to figure out the perimeter of something. Okay? For 2 similar shapes, I should say. Okay. How do I want to do this? I hate erasing this. I really do. Let me bring another whiteboard over. Just bring this guy over. There we go. Okay, and we're going to do this problem right here. Okay, so here we go. Because of these congruency marks, if this is 8, I know this is 8. I think that's it, huh? I don't think, in fact, let me just double check. I'm sorry. This is a 3, which makes this guy 3. There was one more measurement. I'm like, wait a minute. I need something else. All right. Now, knowing what I know here, look at this example real quick. 4 is similar to 2, right? So the scale factor between these 2 sides is the same scale factor as its perimeters. We can conclude that this works, right? 2 equals 2. Okay? So this is the perimeters. That's just 2 side lengths, which still gives me the scale factor. Now over here, I'm going to do the same thing, okay? What I'm going to do is I'm going to pick 2 sides. That's going to be my scale factor, okay? And I apologize, I missed one more measurement. This. Those are 4s. Man, you would think I can copy my notes down right on the whiteboard. Apparently I can't. So I apologize for interrupting the thought that I was explaining. So what I'm going to do, I know that 4 and 3 are similar to each other, right? So I could take that scale factor and set it equal to the perimeters. And my goal is to figure out what the perimeter of this guy is. Now I could do that by but dividing by the scale factor with 8 to get these 2 measurements. not really a difficult concept. Do the same thing with 6 to get the bottom measurement. But I'm going to use what I just discovered here to figure it out. Now, what is the perimeter of this guy going to be? Well, 6 and 4 is 10, 18, 26, 30, right? I think this, it would be 30 for that guy. So 30, and I don't know the perimeter of this guy yet. I'm trying to figure it out. So this fraction is the scale factor of these two similar shapes, and then this one is the perimeters, okay? Which we established before that they should be the same. Cross multiply, we get 4x equals 90, right? 3 times 30, 4 times x, okay? And we get x to be 22.5. So this would be the perimeter of the smaller polygon. Okay? That's it. So we know what the perimeter of this guy is without actually using the scale factor and finding the other two side lengths and adding them all up. It just comes down to this. And I think the greatest thing about geometry is just come up with an example, okay? We can come up with this basic example to see the behavior working here. Now, the proof matches this, right? And then we can use that information to apply it. So kind of a nice workup to it, huh? Once again, I have other examples in my notes. Please look at it and try out the problems, okay? See if you get the same answers, which, hey, hopefully you do. But that's it. So some applications. More importantly is the perimeter concept here. I want to make sure you understand that. But until next time, guys, I will see you all in the next lesson video. Take care.